So today, okay, we're going to go over scalars and vectors. Okay, scalars and vectors are measured quantities. Okay, they differ in that they express similar information from slightly different points of view. Okay, that's really what we're looking at here. All right, so there's many ways of measuring how far apart or how fast objects are going. Okay, sometimes we need to measure them in a scalar fashion, which just means we need to know essentially how big. Okay. And sometimes we need to measure them in a vector manner, which means we need to know how big and in what direction. So if you can imagine that, if I, let's say, ask or try and tell somebody who's never been to Alberta before, they just show up in Okotoks with no sense of, where anything is. And I say, oh yeah, Calgary's just, it's just 35 kilometers from here. How useful is that to them? Well, I didn't say they were from the States, though. Okay, how useful is that? Not useful, especially if they don't know the language and someone just translated what I said for them, because then they're not going to understand the signs either. Okay, so I've got to give them a more accurate, well, not so much more accurate, but I have to give them a more descriptive description of where Calgary is. Okay, everybody follow me there? All right, the other thing we got to look at today is that the way we as North Americans look at distance is really messed up. Okay, we have this cultural problem with how we express where things are. Okay, so for example, if I ask Erica how far it is to Edmonton, how far is it?
2 hours.
2 hours, 3 hours. How many of you were thinking the same thing? What did I ask? I asked how far it is. I never asked how long it takes to get there, but that's how we think. It's automatic, it's ingrained, and it's sad, okay? Because it's wrong, okay? We think about how far places are by how long it takes us to get there. And that's not right, because how long it takes us to get there is dependent on a lot of things, okay? Sometimes you can get to Edmonton in 2 hours if the police are all asleep and you have a very fast car, okay? And sometimes it takes 3 hours, and sometimes it takes 8, okay? Believe it or not, sometimes it takes that long. Okay, we came back from a physics 20 trip to Edmonton one time, and we left Edmonton at 4:30, and we got home at 3:30 in the morning. Okay, yeah, because road conditions can change. Right? They're unpredictable. We know that. We live in Canada. Okay, so when we say to somebody, yeah, it's only 3 hours to Edmonton, that isn't right. Under certain conditions, it's 3 hours, yes. Okay, that's how long it takes to get there, but that's not how far it is. Edmonton is about 300 kilometers from here, and that's not going to change anytime soon, or ever really, because, well, I mean, I suppose the cities grow. You could say that from the outskirts to the outskirts would be less, but center to center, okay, let's say about 300 kilometers. Unless the continent breaks in half right between Edmonton and Calgary, that distance isn't going to change. Everybody follow? Right. So some expressions of distance are accurate and constant, and others are variable. Okay, time is variable. All right, we need to be able to tell the difference between distance, displacement, speed, and velocity, because probably up till now you use the term speed and velocity interchangeably. All right, but they're not exactly the same thing. They do both express how far you go in a set space of time, but one of them will also express what direction you're going. The other will not. Okay? For example, no one has ever received a velocitying ticket. You might get a speeding ticket, but you're never going to get a velocitying ticket. Okay? Because speed is a scalar quantity. The police only care that you were going way faster than you were supposed to, not what direction you were going, unless you were on the wrong side of the road and going against traffic, but that's a separate ticket. Okay? They don't give you a velocitying ticket for going too fast in the wrong direction. It's two separate tickets, and you're in really big trouble if that happens. Okay, so speed is a scalar quantity. It only tells people how fast you are going, whereas velocity tells them how fast and in what direction. Distance and displacement are the same. Okay, distance just tells people how far something is. Edmonton is 300 kilometers from here. Okay, displacement is how far and in what direction. It's 300 kilometers northwest, slightly northwest from here. Okay, sorry, northeast from here, not northwest, northeast. Everybody follow? Okay. And then we'll be solving some problems related to motion. So we will be going over the use of this formula and this formula. No, I haven't lost my mind. Those are two different formulas. Okay, because the one on the left deals with distance and speed, whereas the one on the right that has, these are arrows, by the way. That's how we draw arrows in physics. They only have a tab on the top. Yes, those are D's. They're supposed to be D's. They're D's. Okay, if I fix them, they'll look worse. Okay, displacement and velocity, okay, are part of this one. They're vector quantities. What's time? Is time scalar or vector? Scalar. Okay, as far as we know, time only goes one way. Okay, unless you have a time machine at home. Okay, if you have a time machine at home, let's talk. Okay, there are a few things in my life I would do differently when given a second chance. Okay, so if you got a time machine, then maybe you know something I don't. But as far as we know, time only goes forwards. Okay, keep that in mind. When we start talking about graphing, sometimes people make graphs that say they go back in time. You have to watch out for that. Okay, so you got to just make sure you're not doing that. Okay, all right, so let's move on here. Okay, so if you've ever gone hiking, okay, off trail, like just kind of bushwhacking with no directions, okay, you know that the way we express distance in common usage in North America is only good at getting you hopelessly lost. Okay, if I'm, let's say, using this map, because this is a backpacking trip my dad and I did a number of years ago. Let's say I want to go from Seldom Inn Campground to Snake Indian Falls Campground. Okay. When I leave Seldom Inn Campground, there's a sign that says Snake Indian Falls Campground, 28 kilometers. Did it give me a distance or a displacement? It gave me a distance. Okay. Or no. I'm getting at that as well as something else. That sign is making an assumption. The assumption is that I'm going to what? I'm going to follow the trail. Okay, I'm going to do this. All right, that's the assumption it's making. All our signs assume that, right? When it says Calgary 35 kilometers, it assumes we're going to stay on the road. Okay, if I had a helicopter, I would just go in a straight line. And my displacement would be less because displacement is always a straight line distance and direction between two places, whereas distance might be the path I actually had to follow, which contained many different directions to get from A to B. Everybody kind of follow me there? Right? Because sure, this would be shorter, okay? If I just said, hey, Dad, let's pull out our compass and take a bearing and just do this. That would be shorter. It wouldn't be faster. Why not? I'd be bushwhacking, first off, there's no trail. And secondly, there's all manner of disaster along this path. Okay? There are a whole bunch of rivers, which when I take the path are crossed by, well, you hope anyway. The year we went, a bunch of them were washed out. So maybe this would have been. But there's also this glacier here. That's a bit of a problem. You don't walk across a glacier in the summertime. Crevasses. Okay? There can be snow blown across the crevasse in the wintertime, so you can't see it. Right? But as it melts, it gets thinner, but you don't see that from the top. You just step on it and fall into your death. Okay? So you don't want to do that. Okay? The sign assumes I'm going to follow the path. Okay, that means my direction will change a whole bunch. That's why no direction was given. That's how far I'll have to travel to get from A to B. All right, everybody okay with that? Because T is scalar. Only vector quantities get the arrow over top. Yeah? Okay, so does that sort of make sense? So there's a time and a place for vector quantities, and there's a time and a place for scalar quantities. Obviously, signage, when there's a proper path to follow, is an okay time for a scalar quantity to be used. Okay, but if I'm a pilot, I don't want to use a scalar quantity. Okay, I don't want to say, oh yeah, London is only, I don't know how many kilometers from Calgary, but a lot. Okay, how many choices do I have for what direction to go? 360, right? I have 360 choices, every degree in the circle, okay, going all the way around from north all the way back to north again. I don't like my chances of picking the right one, okay, because probably only one would actually get me there. Now, if I was in Okotoks and going to Calgary, okay, well, probably maybe 20 or 25 of those degrees would at least end up in some part of Calgary because it's pretty spread out and we're pretty close, okay? Well, they can, but they try not to as much as possible unless there's something they have to avoid, right? If there's suddenly a big storm and they want to avoid it. But most of the time, they're going to fly in a pretty straight path from one to the other. Okay? Okay? Same thing with being on the ocean, right? There's no roads or paths to follow. You kind of have to take a heading, and then sometimes the current pushes you, wind pushes you, whatever. You got to take a new heading, okay? Head in a slightly different direction, but you're always trying to go in as straight a line as possible. Okay? There's no road to follow, so a scalar description is not going to be a good thing in that situation. All right, so if we say Calgary is 40 kilometers away, we make no reference to which direction Calgary is. We just get on the road and follow it there. Okay, that's a scalar description of where Calgary is. Okay, and we've only said how far it is, not in what direction it is. Okay, it's still accurate to say that Calgary is 40 kilometers away. Okay. Now, if I say instead that Calgary is 40 kilometers at, let's say, 13 degrees west of north, is that any more accurate? Actually, it's not more accurate. It's more descriptive, but it's not more accurate. Accuracy comes from your measurement. I said 40 kilometers and 40 kilometers. That's accurate to plus or minus 1 kilometer. Okay? If I say it's 40 kilometers, the uncertainty lies in the last measured value. Okay? So I'm sure that Calgary is somewhere between 39 and 41 kilometers from here when I say 40 kilometers. Okay? Had I said it's 40.1 kilometers, now I'm accurate to plus or minus, 0.1 or 100 meters. Okay? Now I'm saying Calgary is somewhere between 40 and 40.2 kilometers. That's more accurate than this measurement. Okay? So accuracy comes from how you measure the value, not whether you put a direction on it or not. Putting a direction on it makes it more descriptive, but it doesn't make it more accurate. Okay? That's an important thing to remember. Measurement determines accuracy. All right, so let's use this example right here. So let's say that I'm going from my house to Walmart. Okay, so if I'm going to go from my house to Walmart, and I don't own a helicopter, because if I owned a helicopter, I wouldn't shop at Walmart. I think that's a given, right? Yes. Yeah. Okay. All right. So I follow the road or the path or whatever. I just kind of drew a squiggly line because you can't. There's no straight lines unless you live right behind Walmart, and then it's not 4 kilometers. So okay. But I just follow a path, okay, whatever path gets me there. I have to make a few turns or whatever. And I arrive at Walmart and I've traveled 4 kilometers. Okay? Is that distance or displacement? That's distance. Okay? Now, in a straight line, I have only displaced myself 2.8 kilometers at 38 degrees north of west from my house. Okay? Since I displaced myself that far, that's my displacement. Okay, so displacement tells you how far and in what direction in a straight line you are from A to B. I do. Yes. They are describing the same trip from different points of view. Yeah. Okay. Now, here's where it gets weird. Let's say that that trip takes me a half an hour. How fast was I going? Nope. Remember, I walked this path to Walmart. As a result of that, I ended up 2.8 kilometers at 38 degrees north of west from my house. They take the same amount of time because I went from here to here. Okay? I didn't follow this path though. Okay? This is what I ended up doing as a result of the blue path. Okay? Right? I mean, they always say the shortest path between 2 points is a straight line. That's displacement. But you can't always go on a straight line. Had I gone on a straight line, that's how far it would have been. Okay? Bernardo. I would be moving at 8 kilometers per hour. Okay, so here's how Bernardo figured that out. He doesn't know it yet, but this is how he did it. Okay, V equals d over t. Okay, how fast is asking for speed? How fast and in what direction is asking for velocity? Okay, I asked for how fast. So that means I take the distance, 4.0 kilometers, and I divide it by the time, 1/2 of an hour. Well, 4 divided by 1/2 is 8 kilometers per hour. Okay, because I got kilometers on the top and hours on the bottom. You can't divide kilometers and hours and make them cancel, so you get them both, kilometers over hours. Okay, half an hour. Took me a half an hour. Okay, now if I want to calculate my velocity, what am I going to do? I'm going to do the same thing, except I'm going to use displacement over time instead of distance. Okay, the time is the same for both, okay, because it's the same trip from 2 different points of view. So I'm going to take my 2.8 kilometers at 38 degrees north of west, got to put all that in there, okay, divided by 0.5 hours, which means my overall velocity is 5.6 kilometers per hour at 38 degrees north of west. Your displacement and your velocity will always have the same direction. Okay? They have to. You can't end up with a displacement 38 degrees north of west by traveling at a velocity south. Okay? Going south would never end up, you'd never end up over there. Okay? That sort of make sense? Okay. Oh, I could, but in this case, that's an extra calculation I don't need to do. Most of the time in this unit, we're going to get meters and seconds. So it'll be meters per second. That's what we use for velocity most of the time. Okay, I'm just using kilometers per hour because you're more familiar with that. Yeah. Okay, so now let's say, because I'm old and kind of losing my mind, I get to Walmart and realize just as I get to the door, I forgot my wallet, because that's never happened to me. Okay, all right. So I can't buy anything. I'm not going to go into Wally World for nothing, so I turn around and walk home. Okay. Well, I follow exactly the same path home because I'm a creature of habit, and it takes me exactly a half an hour to get home. What's my speed over the whole trip? It's exactly the same. Yeah. Okay. It's still 8 kilometers per hour. Okay. Sorry, speed, so no arrow over top. Okay. Now my total distance is 8 kilometers. Okay. And my time is 1 hour. So I still get 8 kilometers per hour. Okay. I walked the same path, same distance, same rate. It took me the same amount of time, so it's 8 kilometers per hour both ways. Okay. But what's my velocity? I went to Walmart and I went right back home again. But I want it over the whole trip. What's my average velocity there and back? Exactly. My overall velocity is 0 because I have no displacement. If I end up back where I started, my position hasn't changed. Okay, I haven't displaced myself from my starting position if I end up back there. You guys follow me on that one? Okay, so when we look at displacement, okay, displacement is actually calculated by taking the final position of an object and subtracting the initial position of the object. All right, so if they're the same number, that comes out to 0, okay, which is why my overall velocity there and back, so to Walmart and back home, ends up being 0. Okay, because my displacement is 0. Okay, and there's no direction on that. There can't be because I didn't go anywhere. Right, I'm still back in the same spot. Final position, so position final, position initial. Okay, this is why, guys, the odometer on your car, okay, that tells you how many kilometers are on your car, reads which, distance or displacement? Yeah. What good would it be if it read displacement? Well, what would it read every time you came home? No, it would read how far it was from the dealership you bought it at to your house. Come on, people. I get everybody with that one. No one ever says that. I get everybody every year. That's one of my go-to jokes. Okay. Yes. Okay. Because remember, velocity is a vector quantity. It only cares how far in a straight line and how fast, right? In a straight line, I still ended up back at home. Yeah. Okay. So my displacement is still 0. My final position and initial position are the same. Okay. My distance, you're right, is 8 kilometers. I walked 8 kilometers to accomplish nothing. Right. Okay. Is that making some sense to people? All right. Now, when it comes to manipulating the equations, okay, so we got 3 rules of algebra here. Okay, we need to write these. Well, we know 2 of them already because we used them on the mole equation, but the third one's going to come into play here. Okay, so we'll call that manipulation because it's going to become important. Okay, so to move something, we do the opposite operation. Okay, so if I need to move something that's being added, I'm going to subtract it. If I need to move something that's being divided, I'm going to multiply it. Okay, if I subtract something from one side of an equation, I have to subtract it from the other side. Okay, that's the second rule. If I multiply something, I got to multiply the other side. Okay, so those ones we used when we used the mole equation. Now comes the third rule. Okay, and the third rule is it's not difficult. Okay. Whoop. If I'm solving for something, I want to move what's not attached to it first. Okay, and I'll explain what I mean by attached here in just a minute. Exactly. Okay, so actually we'll use that example. Okay, actually no, we won't. We'll use this because it's pretty much the same thing, and it's a formula you're going to need later on in this unit. How many people have seen that formula already in math? Okay, good. Who's math class you in? Whose math class are you in that's taught you y equals mx plus b already? Oh, you learned it last year? Awesome. Okay, for those of you that haven't, don't worry, it's not hard. Okay, this is the graphing equation. Okay, so this is an equation that's used to solve for the slope of a line on a graph. Okay, and we'll get to that. That's part of what we're going to be going over this week. Okay, if I want to manipulate this and solve for m, okay, right now x is attached to m. Okay, it's right beside it. It's being directly multiplied by m. So b is not attached to m. So if I want to solve for m, I'm going to move b first. B is not attached. So I'm adding b right now. If I want to move it, I need to subtract. Okay, so I'm going to subtract b from both sides, and that's going to end up like this. Y minus b equals m times x. All right, now that I've moved what's not attached, now I can move what is attached. How do I move x? Divide by x, right? Now I've solved for m. Okay, was that very hard? I have to remember 3 rules. Okay, and we know 2 of them already. If I want to move something, I do the opposite. What I do to one side, I do to the other, and I move what's not attached first. Guys, those 3 rules got me through university physics. Okay, they can get you through high school science, no problem. All right, as long as you remember those 3 rules of algebra, no mathematical equation should give you any trouble. You may. All right, everybody okay with that? So the formula we're going to be manipulating the most for the next little while is this. V equals d over t. All right, so if I want to manipulate and solve for d, what do I have to do? Right, multiply both sides by t. That's just like what we did with the mole equation. Okay, so I multiply both sides by t. T comes over here. Done. Okay, let's say, I had a better way of doing that before, but that's okay. Let's say instead of that, I want to solve for t. Multiply by what? D? But d is on the top. If I want to get rid of d, I'd have to divide by it, right? Okay, now that's what most people say the first time we do this. But look at what happens if I divide both sides by d. What's d divided by d? 1. So when I do that, I'm left with 1 over t. Is that the same as t? No. When we're solving for something, we want it to be on the top of an equation. Okay, so to solve for t, it's better to do it with kind of 2 steps. That is, multiply both sides by t. Okay? Now what do I do with v? Divide by v. Now t's on the top when I solve for it. Okay? I'm solving for t instead of 1 over t. And there's a big difference. Okay? Solving for 1 over t, you're going to probably get like a really tiny decimal. Solving for t, you're going to get a real number. Okay? Everybody going to follow there? That's the one manipulation we didn't have to do of the mole equation. Okay? Because that was solving for n. Right? Well, whatever the units for time are. Yeah, I'll give you a unit of time, right? Because it's either kilometers per hour or meters per second or whatever. Yeah. The vector quantities. Okay, so right, and then same with the d's, right? This is displacement. I'm going to give you guys a formula sheet, so I need to distance. Okay, the little arrow just denotes that it's a vector quantity. You'll see that if you take physics, you'll see basically, well, at least 3/4 of your variables are going to have that arrow over top of them, right? Like acceleration is a vector quantity; it has an arrow over top of it.
When you put like a marble in a glass of water, the water is displaced. Is that the same thing for displacement?
Displace means to move its value. Okay, so when you put a marble in water, it displaces, it moves some of the water out of the way, which is why it looks like the volume changes, right? So it displaces some and it moves up. It has to because it takes up space. So displacement means to move something.
Do you have to, like, if you're talking about the water moving, do you have to see the direction?
No, you're looking there at displacement in terms not in terms of what we're talking about here. I know that it's using the same word for 2 different things, but yeah. I mean, you could say the water was displaced upwards in the tube, right? Because essentially it was. The marble sinks to the bottom, right? All right. Okay, so scalars and vectors like we talked about here, okay, and this says more accurate, but I think I changed it in your notes to say more descriptive, is that right? If I didn't, you need to change it. If you got them, I'm pretty sure I changed it in your notes package. Okay, basically, the reason I want to do that is because I just said it was more accurate to put a direction on, which it isn't. Okay, it's more descriptive to put a direction on, but this 40 kilometers is just as accurate as the scalar 40 kilometers that I measured. Okay. All right, now vectors are not always measured in degrees. In fact, we won't use compass directions at all unless they're directly opposing each other, right? So you're never going to have to use the like sine, cos, and tan, okay, in science 10. It is the very first thing we do in physics 20, right? So trigonometry is huge in physics 20, but we won't require you to do any trig in science 10. So we're only going to deal with what's called one-dimensional motion: forward, backward, left, right, up, down, east, west, north, south. I'm running out of things now, okay? But it's always going to be directly opposed, okay? We call that one-dimensional because it never veers to the side. Okay? All right. So when we give a distance the object has traveled, we're giving it a scalar quantity. Like I said, it was 4 kilometers from my house to Walmart, but the displacement for the same trip is 2.8 kilometers at 38 degrees north of west. Okay, so distance and displacement are different measures of the same thing. Okay, it was the same trip looked at from different points of view. Okay, everyone kind of follow that? What I mean by different points of view? All right. Well, you actually have to travel 4 kilometers to get to Walmart. Like we say, you only ended up 2.8 kilometers in a straight line from where you started. Okay, and we talked about this already. We calculated the speed, and then we calculated the velocity. Okay, and then we found out that if we went home by the same route, our overall displacement would be 0, and our overall velocity would be 0. Okay, but our distance and speed, okay, wouldn't change. Well, the distance would change. It'd be 8 kilometers, but the speed wouldn't. There was the slide I was looking for. Okay. I want you guys, let's go over this one together. Let's calculate how far a deer running at 15 meters per second would travel in 45 seconds. Oh, yeah. People can run that fast. Usain Bolt runs at about 17.4 meters per second at his top speed. Okay, not his average speed, as his top speed. Okay, he does spend a majority of the race accelerating. Well, not anymore. He's done now. But all right. What did the question give me? It gave me time. Okay, 45 seconds. What else did it give me? It gave me speed. How do I know that wasn't a velocity? Right. There's no direction on it. What do they want me to calculate? Displacement or distance? Distance. I can't calculate displacement. I don't have any directions. I can't calculate displacement without a direction here. Okay. Usually when it says how far, that's saying just distance. If it says how far and in what direction, that's displacement. Okay. So we're looking for D. So this is the formula we're going to have to use. V equals D over T. So if I'm going to solve for D, what do I have to do with T? Yeah, multiply both sides by T. All right, so T times V equals D. All right, so when we plug in our numbers here, that's going to be 15 meters per second times our 45 seconds. Times 45. All right, so 675 meters. That's impressive. But if you've ever seen a deer at full clip, they can move pretty fast. Okay, if you spook them, they can move pretty fast. The ones in town don't care. If you ever noticed that, you can just about walk up and pet them. Yes, and let's have a look at that because that's a good question. So how did I arrive at the units? Well, I arrived at the units because I know that distance is measured in meters. But okay, mathematically speaking, here's what we did. We multiplied meters per second by seconds, which is the same as saying seconds over 1. Everybody okay with that? So if I multiply this out, I get meter seconds per second. Well, the seconds cancel and I'm left with meters because a meter seconds, I don't know, that's a momentum thing. I think it's nothing we would use. Okay, everyone okay with that? Okay. You can always check if you've manipulated right by doing this. Okay, this is what we call a unit analysis. Okay, you can look at the units, do the same operation, and see if you get the right units. If you don't get the right units, you probably manipulated it wrong. Okay. All right, questions on how that one worked? Okay, give this one a try. How long will it take a tortoise to crawl 200 meters at a speed of nothing? Well, forever. That's how long. I don't know what happened there, but I was missing something on that question. Okay, I'll give you a minute on that one. Okay, so for this one here, we're given V. Okay, we're told it's 0.25 meters per second. Okay, and we're told the distance is 200 meters. All right, we're looking for how long that takes. How long is always time. Okay, so V equals d over t. And I'm solving for t this time. I can't solve for t if it's on the bottom. So I'm going to multiply both sides by t, and then I'm going to divide both sides by v. Okay, so I'll end up with t equals d over v, 200 meters divided by 0.25 should give me 800 seconds, right? All right, that's a long time. Okay, but a tortoise doesn't move very fast on land. Okay. Just pick it up and carry it. Although if it's a giant tortoise, good luck with that. They weigh like as much as a Volkswagen. Okay.
Would you ever want, like, because 800 seconds, most people can't read that as time. Do you want us to make it?
Nope. Unless I ask for it specifically in a certain unit, you keep it in what units I give you. Yeah. So that's a good question, guys. I know, like right now, you're going 800 seconds. Nobody knows how long that is. Well, I do. And that's okay. And you will too. Okay. If you're doing extra conversions, first off, I probably don't have that keyed. If you're doing an assignment or a test, I probably don't have it on my key in minutes. And then I'll have to figure it out, and that'll take me more time. And secondly, it's an extra calculation. And every time you bring in an extra calculation, there's a chance you punch something on the calculator wrong. It's not that you would do it wrong, but you punch something on the calculator wrong and you make a mistake. Okay? Unless it says specifically how long in minutes, leave it in whatever I gave you. Okay? It saves you time. Don't do it. Just don't. Yeah. Unless I specifically ask, keep it in whatever units I gave you.
So why did you do all the manipulating for meters?
Just the way I do it. I find it easier to manipulate when they're letters than when they're numbers, right? Especially the way I put the numbers in where I didn't put the units on, right? It's easy to forget. Was that seconds or meters per second? I don't remember. Okay. Whereas if it's D, I find that I can remember what everything was better that way. If you want to plug the numbers in and then manipulate, you go right ahead. Whichever way makes more sense to you, mathematically, they are no different. Okay, so if you want to put the numbers in and then manipulate, go right ahead. I'll understand that when I'm going over your stuff. Okay. Okay, now this is one where direction now matters. Okay, so we'll go over this one again. I'm gonna give you a minute to write it down, okay, because it's a good vector example, but we're gonna go over it here in a minute. Okay, so to calculate average velocity or average speed, okay, we're gonna take the total distance or displacement, whichever we're using. In this case, it'll be displacement. The total displacement divided by the total time. Okay, everybody with me there? Now there's two different parts to this trip. There's part one where they went north, and then there's part two where they went south. Okay, so what I'm going to do is break this up into those parts. And then I'm going to have a total as well. Okay, the total is where I'll get the average velocity over the whole trip. Okay, in part one, I know that the displacement is 100 kilometers north. And I know that that takes 1.2 hours. Okay, and then in part two, I know that the displacement is 62 kilometers south, and that that takes 0.9 hours. Okay, so what I have to keep in mind here is this. My average velocity is my total displacement over my total time. What are you looking at? Oh, okay. It's my total displacement over my total time. Okay, that's what I'm looking at. So to calculate my total displacement, I'm going to take the displacements from these two things and add them up. But what do I have to keep in mind when I add them up? Yeah, they're directions. One's north and one's south. How can I represent that numerically? Positive and negative. Okay, so I'm just going to say then that my average velocity is 100 plus negative 62 or minus 62, whichever, it's the same thing. Okay, divided by 1.2 plus 0.9. Why didn't I make the 0.9 negative? Because it's time, right? Time is scalar. If I write negative 0.9, it means I went back in time. Okay, and I didn't do that. Yes, it should have an arrow. You're right. Well, unless you had like south and south and south, then you could make it positive. But if you have north and south, you have to pick, right? Usually north and east are positive, south and west are negative. Because when you put them on a like a XY graph, this is negative and this is negative, this is positive and this is positive, right? Right, so that's why we typically do it that way. Okay, so I'm going to have 38 kilometers north on the top. Okay, and I'm going to have 2.1 hours on the bottom. VAV, average velocity, right? So that's subscript VAV. All right, so now when I do that, I should be able to calculate what my average velocity was. Okay, so 38 divided by 2.1 gives me 18.1 kilometers per hour north. Right, I have to have a direction on that. Okay, would you lose a mark if you didn't have the north on there?
Probably.
You would definitely. Not a half mark either. Okay, if it doesn't have a vector or the right vector, it's wrong. Kilometers per hour north, yeah. Okay, now it's usually at this point that somebody asks, well, Mr. Coder, couldn't I just calculate the velocity here and the velocity here and add them together and divide by 2? And the answer is you could do that, but it would be wrong. Because if you do that, you're treating these two parts of the trip like they're what? Like they're equal. Are these equal? No, they're not. They don't represent equal portions of the trip in either displacement traveled or in time. Okay, you could do that if you had two parts that represented exactly equal parts of the trip. Then you could do that. Okay, but 99.9% of the time, that's not the case. Okay, and you'd have to go total displacement over total time. Or if this was about average speed, okay, how would this differ? How would I change this if I wanted to calculate the average speed? Sorry, you had a question. Go ahead, ask your question.
So how do you calculate it if you have a north and then you go like west or?
Okay, that's what we do in physics 20. Okay, so you'd go north and then you'd go west. Okay, so your average would be this, and that would require trig. Okay, so you do Pythagorean Theorem to get the hypotenuse, trigonometry to get the direction. Yeah, that's what we do in physics 20, like first day. Thanks, Star. Did you grab your phone?
Yeah.
Okay. All right, so does that make sense?
You were asking about total.
Yes, if I want to calculate average speed, so what do I do?
You would add together the kilometers and then you would add together the time.
Yeah, exactly. Direction isn't a factor if I'm asking for speed because it's scalar. I would have then 162 over 2.1, okay, and then I would get my speed that way. All right, everybody follow? When you're dealing with speed or you're dealing with distance, everything's positive, okay, because direction doesn't matter. Yes. right? Because we know we went slower than that in part 2, right? It's the average over the whole trip, okay? And that's where that whole like averaging the velocities thing doesn't work. That would be like me saying I drove from Calgary to Edmonton, and for the the first 290 kilometers, I was able to go 110 kilometers per hour. But there was a bit of construction in the last 10 kilometers, and I had to go slower. Well, does that mean that I should go this plus this divided by 2? No, they don't represent equal parts of the trip. My average is going to be way closer to 110 than it is to the 50 I had to go in the construction zone, right? So I have to weight that average by saying, look, most of the trip was this, okay? And that's what we do by doing it this way, okay? We weight it in favor of the parts of the trip that count more. Yeah, yeah, exactly. Because we made north positive and we made south negative, and our answer came out positive, which means we ended up north, right? Because we went 100 kilometers north and then 62 south. So we still ended up north of where we started. No, that's again where you would have to do the Pythagorean theorem. Okay, so I would have this, and then I would use the angle. The angle would take into account that part of it, and Pythagorean theorem would take into account the length of the arrows.
So 38 kilometers, like that's also like, could you say that like if it was negative 38 or something, like if you came up with a negative number, could you just like switch it over, like say it was negative 38 more, you just say 38 south?
Yep, you'd say 38 south then. If it came out as negative 38, then it would be 38 south because we assigned negative to south. Yeah?
When you do the 100 plus negative 62,
Mm-hmm.
you just put the negative 62 in brackets instead of doing it like that.
You can do it however you want. You could have just done this too. Well, not that. Minus. You could just go minus. Yeah, either way. Whatever makes sense to you. Okay. Any other questions on that one? All right. So things to remember here. Scalar quantities have magnitude only. All right. So other scalar quantities, distance is a scalar quantity, mass. Okay. Mass is a scalar quantity. How much matter you possess is your mass. That doesn't have a direction. Weight does. Yeah, because weight is the force of gravity pulling on your mass. They're two different things. If you thought they were the same, that's one of the other North American problems we have, is that people say weight and mass are the same thing, and they're not. Okay, I could lose weight just by going to the moon. I would weigh 1/6 what I weigh here, but I'd be just as fat there as I am here. So, okay, it doesn't actually change anything. There's just as much of me there. There's just less gravity to pull on me, okay, which would be cool because then I could jump high again like I could in my youth. But yeah, apparently the spacesuit really inhibits that. I don't know. Okay, time, scalar. Okay, time only goes forward. Okay, vector quantities, displacement, velocity, acceleration is going to be a vector quantity that we're going to use. Okay, things like that. Force, which we don't use much as a vector quantity, but energy and work are scalar. Okay. All right. And we did a deer question already. Okay, I want you guys to try that one. How long it'll take a jet traveling 330 meters per second to go 400 kilometers? Okay, so how long it takes a jet, we're looking for time. Okay, because it asked us how long. It gave us a speed, 330 meters per second, and it gave us a distance, 400 kilometers. What's our problem here? Different units. Okay, which would be easier? Convert the kilometers to meters or convert meters per second to kilometers per hour? Yeah, do this one. Convert kilometers to meters. Way easier. Multiply by? Oh. No, there's more meters, right? There's 1,000 meters in a kilometer. I need to multiply by. Okay, metric system. Okay, we got to make sure we know our metric system. There is one of these in the front of your notes package. Okay, you need to know the metric system. It's got to be automatic. No one's made you memorize it, and that's wrong. You got to memorize it. You got to know the metric system like that. Okay, all right. So this is going to be then 400,000 meters. Okay, so we've got V equals d over t, and we're solving for t. So we're going to multiply both sides by t, divide both sides by v. Okay, so t equals 400,000 meters divided by 330 meters per second. So our units for time are going to end up being seconds, okay, and that's fine. All right, it's going to take 1,212 seconds.
Do you really care if we did it in meters or kilometers? Because I did it in kilometers and it got
You converted it to kilometers per second?
Yeah.
So you went 0.330? That's fine. Yeah. Okay, any other questions on that one? All right.
Just get it without converting them, multiple units by 1,000.
As long as you remember to do that conversion at some point. I usually say you should convert in your givens before doing any math, because when you start getting into multi-step problems, it's easy to forget to do it later. Okay. Okay. I want you guys to try number 4 here. Elevator travels, I don't know if we'll get done it yet, but okay, elevator travels up 85 meters in 30 seconds and then down 60 meters in 20 seconds. Average speed, average velocity.